Next speaker is Studzińska from University of Studzińska, and this is the title of the talk.
Thank you. I wish to present to you our result. We are investigating differential rotating neutron stars. I'm working in cooperation with Opava, and Marcus. How we are describing the differential rotation. Differential rotation occurs when neutron stars are just after taper, when they are hot, or after merging in binary system when the angular velocities is different. It depends on the layers in the star. The rigid rotation is when the angular velocity is the same in different layers. So we are investigating rigid rotation as well differential rotation. Especially we are searching a maximum mass of differential rotating neutron stars, and it is important for how to distinguish a black hole from neutron star. If we have an observation in binary system, by observation we can provide information about masses of the objects which we observe. And if we know about maximum allowed mass which neutron star could have, we know how to distinguish a neutron star from a low mass black hole, a stellar black hole. Theoretical models predict that the maximum mass of non-rotating neutron star is to be in the range of 1.5 to 2.5, and it depends on the equation of state which we are assuming. For a given equation of state of rigidly rotating neutron star, neutron star can have even mass even 12 to 20% higher than maximum mass for the non-rotating case. But the most effective process which can increase maximum mass is differential rotation, which is much more efficient in this, and maximum mass could be much more higher than for non-rotating case, and I will show you how much higher it could be for differential rotation than for non-rotating case. The second thing, which is important for the astrophysical way, is making some limits on the equation of states. We have several models of equation of state, and depending on equation of state, we have mass and radius from the equation of state. And if we have maximum mass for a given equation of state, and if we by observation can measure mass of the compact star, and if this measured mass is higher than the maximum mass for the given equation of state, we can exclude this equation of state for theoretical way. So in our work, we use fully relativistic code based on multi-domain spectral method developed by Ansel, Studzińska, and Leon in 2009. We study axisymmetric and rigidly rotating as well differential rotating neutron stars. We assume the simplest equation of state, the polytropic equation of state, where P is pressure, K is polytropic constant. In our work we use 1, is the easiest way. Rho is density, and gamma is polytropic index. We adopt a simple rotation law introduced by Komatsu in 1989, where F is function of rotation, omega is angular velocity in the star, and omega c is the central angular velocity. We use in our work normalized degree of the differential rotation, A tilde. And for rigid rotation, A tilde goes to 0, and the higher A tilde, the higher is degree of differential rotation, and the steeper profile of differential rotation. So this profile, differential rotation profile is for the rigid rotation. So this line is straight, yeah. And this profile is much more steeper because here we have differential rotation. Okay, this is the previous calculations for rotating neutron stars made by Baumgarten. So this is the mass, and this is the density. This is the calculations for the non-rotating case. So it described by Thoma-Oppenheimer-Volkoff equation. That's here you see TOV. Here is the rigid rotation case. Here we have, if we go up, the A tilde, A to minus 1 in their work, goes higher, and the higher is degree of differential rotation. This solid lines is result by Studzińska, and the dotted lines is result by Baumgarten in 2000. And as we see, for the small degree of differential rotation, or for the static case, these results are the same. But if we go further, with higher differential rotation, degree of differential rotation, the results are much more different. It was because the code which used Baumgarten has some numerical limits. Code developed by Studzińska et al. Is much more accuracy, and they could obtain much higher masses and types of differential rotation. The types which they discovered was A, B, and C. This is A tilde, so degree of differential rotation, and this is maximum density in the star. And this is the regions, this is areas of existence of these types. So we have existence of type A, existence area of coexistence of type A and B, area of coexistence of type C and D, and area of existence of type C. This black thick line corresponds to the separation line which separates each of the type. How do we find maximum mass for different types? For type A, this is type A. This is the shape which we obtain for type A, and we are searching by by accelerate the star by it gets more oblate. So this is the ratio of polar radius to equatorial radius, and we get it more when it gets lower. Somewhere we find the maximum mass. So this is maximum mass, and this is the ratio, the polar radius to equatorial radius, and the shape is like that, and this is the density profile. No profile. Density profile. This is cross section of the star, because we have the axial symmetric star, and these maximum masses are near mass shedding limit. So this is the moment when the angular velocity is so high that the mass from the star is flying out from, escaping from the equator, and we see these two cusps. Here the mass is flowing out, and this is the point of a maximum mass for this case. And this is depending on the maximum density in the star, maximum mass also. And this is line for static case. This is the line corresponds to the Keplerian limit, so well, the mass shading limit. And the higher lines shows us the higher degree of differential rotation, and this is increasing function of A tilde. So when we increasing degree of differential rotation, the maximum mass grows up. This is the type C. This is the shape which we obtain for this type. So this is some kind of toroidal shaped star. And also, like for the type A, we accelerate the star, getting higher angular velocities, and going to the point near to this ratio, polar radius to equatorial radius, nears to be 0. And this is the similar plot like for the type A. How much time do I get?
5 minutes.
5 minutes, okay. So this is the mass versus maximum density in the star, and the same. We have lines corresponding to the degree of different degree of differential rotation, and these points are the maximum masses. And opposite to the type A, it's a decreasing function of degree of differential rotation. Here we have type B of star, and this is the shape. This is near mass shade limit, and also near toroidal shape with cusps, so the mass are flying out, escaping from the star. And we are searching it by getting through the, we call it beta tilde. It is a parameter which describes the shape of the star. So beta equals 1 means toroidal stars, and beta equals 0 is for mass shading limit. So this star is near the beta tilde equals 0, and we have, depending on the different maximum density, we find maximum mass on one or another arm of this plot, of this lines. And this is also the same similar plot as for the type A and type B, maximum mass versus maximum density. And the same as for type C. Maximum mass is a decreasing function of differential rotation degree. And we found also type D. We were searching, going through the beta tilde, so this shape parameter, and we found that maximum mass is 1 on the arm of the lines. And this is the shape near mass shed limit, because this is also near the mass shed limit. This is the summary of our work for one polytropic equation with gamma equals 2.5, and this is the increasing. This is dimensionless increasing of the maximum mass to the static case, to the non-rotating case, and we can see that this is the maximum mass for the type A is increasing function. For type B and C are decreasing function, and for type D, first it grows up and then goes down. This is the summary for this all our calculations. And here we have static case. Here we have types A, types C's, types B's. So the higher increase of the maximum mass is for the type B's. And the conclusions. The maximum mass of differentially rotating neutron star depends on degree of differential rotation and type of the solution as well as maximum density. Differential rotation could increase maximum allowed mass of neutron star up to even 3.5 times in comparison to maximum mass of non-rotating case. We can see it just here, so almost 3.5 increasing. We have found new types of solution which has not been considered in previous work, so type B and type D. And those types exist only thanks to differential rotation. Without differential rotation, they couldn't exist. And the highest increase, as I mentioned, is for type B of solution. And I said that before that types A, maximum mass is increasing function of differential rotation. For types B and C of solutions, maximum mass is decreasing function of degree of differential rotation, and for type C is firstly increasing function and then decreasing function. So